So let us go for the E2 elimination reaction. So E2, as the name indicates, 2 stands for bimolecular. It is also known as second order elimination reaction. Just like SN2, E2 is also a bimolecular elimination reaction, which generally occurs in presence of strong base. And as it is elimination, we know that a sp3 carbon will be converted into sp2 carbon, or a saturated molecule will be converted into unsaturated. In E2 elimination, it is observed that the rate of the reaction depends on the concentration of both substrate as well as base, and therefore it is called as bimolecular second order reaction. This is a one-step reaction where the base approaches to the beta hydrogen. The bond between carbon and beta hydrogen is broken partially. A bond between a beta carbon and alpha carbon, a pi bond, is partially formed, and simultaneously a bond between alpha carbon and the leaving group is broken. So it goes via a single transition state to give the product where finally the bond between carbon and beta hydrogen is broken, the bond between carbon and leaving group is broken, and a new bond between alpha and beta carbon, that is a pi bond, is formed to give you unsaturated compound as a product. Cope elimination reaction is one of the best example of E2 elimination reaction, and this is one of the example of Cope elimination. Again, you can see here a carbon to carbon double bond is formed due to elimination reaction. If I see the kinetic equation of this particular reaction, I'll find that rate is directly proportional to concentration of substrate as well as base. Because it is a single step, both are involved in that step, that is RDS, or a slow step, and therefore it is bimolecular in nature. So you'll find that you get one first transition state, and then it falls into a product where carbon to carbon double bond is formed. So this is how energy goes on increasing and then decreases to give you the product in E2 elimination. Now, in E2 elimination also, here beta hydrogen is lost along with leaving group. So if you take substrate something like this 2-bromobutane, this is your alpha carbon atom, this is your leaving group, and this particular carbon is flanked by one carbon and second carbon. Now, over here what you'll find that this is CH3 and this is CH2. So these two hydrogen atoms are different, or this is beta 1 carbon, this is beta 2 carbon, and here the hydrogen attached to, let's say, beta 2 are beta 2 hydrogen, and this is beta 1 hydrogen. So which hydrogen is lost? Depend upon that, you'll get the product. So if this particular hydrogen is lost during elimination, if base abstract this particular hydrogen, a double bond will be formed between your beta 2 and alpha carbon atom, and you'll get this as a product, that is 1-butene as a product. If beta 1 is lost, then you'll find that a double bond will be formed between beta 1 and alpha carbon atom, and you'll get this as a product, where now you can see a double bond is between these two carbon atoms, and 2-butene will be obtained as a product. So we are expecting two products. One is 1-butene and another is 2-butene. One is a less substituted, other is a more substituted product. You can see here olefinic carbon atoms are attached to 1, 2 and 3 hydrogen. Here olefinic carbons are attached to 2 hydrogen. So this particular product, since it's more substituted, it is more stable and therefore will be obtained as a major product. You can see here 81% of this particular product is obtained. This product is also called as Sytzeff or Sytzeff. And the other product, which is a less substituted alkene, will be obtained only up to 19%, and this is a less substituted product. This product is known as Hoffmann's product, and more substituted alkene is called as a Sytzeff product. So if you see the example now, what is Hoffmann elimination reaction? So in Hoffmann, what happens now, if you have some leaving group is a bulky leaving group, and we know that even a reaction we had a carbocation, but in E2 it is a single step where substrate and base both are involved in the same step. What we'll find now, a base has to approach to beta hydrogen in order to remove this beta hydrogen. A bond between beta carbon and alpha carbon should be formed, and along with that, a bond between leaving group and alpha carbon should be broken. All these things happen in the same step, and then the transition of state of such kind of reaction becomes highly crowded. When it becomes crowded, if your leaving group is small, then reaction will go in such manner that you will get more substituted alkene as a major product. That is, Sytzeff product will be a major. But if you have something like this quaternary ammonium salt, where this is a very bulky group, at that time reaction will go via a Hoffmann elimination reaction to give you 1-butene as a major product. You can see here, if the base approaches from here, this is a less androxide, terminal hydrogen can be easily removed, but if you come, the base comes from this side, this particular is in the chain, this particular hydrogen atom is attached to a carbon which is inside the chain. So obviously the transition state will be highly crowded, highly unstable if it is coming from this side, and therefore this product will not be obtained as a major product but Hoffmann product, even though the product obtained is less stable because the transition state of this Hoffmann elimination is more stable. This is a kinetically controlled reaction where you get Hoffmann product as a major product. So in Hoffmann elimination, the least substituted or less substituted alkene is obtained as a major product. Why this happens? Because of the steric factor. The transition state over here, because of the leaving group is very large, becomes highly crowded for the Sytzeff reaction, and therefore then this has to come from the less hindered side. If that is so, it will always give you the less substituted alkene as a major product. This is called as your Hoffmann's product or Hoffmann's rule. Already spoken about Sytzeff, which says that highly substituted alkenes are more stable, therefore obtained as a major product. So if I take these alkenes, if these possibilities are there, you know that this particular alkene will be the most stable, and as I go from this alkene to this alkene, you can see the substitution goes on decreasing and the stability of alkene also goes on decreasing. If you have some leaving groups like Nr3 plus, Sr2 plus, they are very bulky leaving groups. At that time, Hoffmann's product will be a major product. But if I replace these groups by halogens, then Hoffmann product will be a minor product. Similarly, if the size of base is large, at that time also Hoffmann product will be favored over Sytzeff product or Sytzeff product. This is because the transition state goes via a very crowding if the base or the leaving groups are bulky, and at that time then Hoffmann product is preferred. So you can see here this particular leaving group is very large. At that time there are two possibilities: hydrogen lost from this carbon or it can be lost from this carbon. If this hydrogen is lost, you get a Sytzeff product. If this hydrogen is lost, you get a Hoffmann product. Hoffmann is a kinetically controlled reaction. Sytzeff is a thermodynamically controlled reaction. In thermodynamically controlled reaction, stability of product becomes important, but in kinetically controlled reaction, stability of intermediate becomes important. Because stability of intermediate in via Hoffmann reaction is more whenever you have a bulkier leaving group, whenever you have a bulkier base, you'll always get Hoffmann product as a major product. So what happens over here? A bond breaking and bond formation both happen simultaneously. It requires, so how it happens? Like, what is the stereochemistry of this particular reaction? So you will find that E2 reaction requires coplanar arrangement of orbitals. How? So we'll find that either you can have anticoplanar or syncoplanar conformation. So if I take this particular base and this reaction is happening, it takes a beta hydrogen, Br goes as a leaving group, and double bond is formed between second and third carbon. Now how they will come? So let's see the stereochemistry of this reaction. So whenever there is an anticoplanar, they are to the opposite side. See, this is your leaving group, this is your beta hydrogen, and a base will be coming from this side. And if it is syncoplanar, then they are to the same side, and then the base has to approach from this side. You can see the steric crowding will be there when there is a syncoplanar transition state. It's an eclipse form, whereas anticoplanar is a staggered form. So syncoplanar is energetically unfavorable because we can see there's a lot of steric repulsion is there, steric hindrance is there, and therefore generally anticoplanar transition state will be favored so that it becomes more stable. In the example here, Br and hydrogen, syncoplanar treated with base, you'll get double bond over here and you get this as a product. Take this example here, one of the hydrogen is lost and cyclohexene will be obtained as a product. So all these are E2 elimination reactions. Take this example now. This is a cyclohexane. Br is a leaving group. Br is equatorial. Okay. So if this chair flips, it gets converted into flipping. We already studied in cyclohexane. This goes up, this comes down. Equatorial becomes axial, and axial becomes equatorial. So Br equatorial becomes Br axial. And whenever they are diaxial now, the beta hydrogen and the leaving group, this particular transition state will be highly stable. It goes in a staggered anticoplanar form, and the reaction, elimination reaction takes place at a faster rate. So if your leaving group and a beta hydrogen, if they are diaxial, 1, 2, diaxial, then the reaction will be fast and you'll get stable product by where the transition state is anticoplanar. Take another example now. If you have two diastereomers, this is SR and this is RR. These two molecules are there. SR, if undergoes elimination, is transalkene as a product. If RR goes into elimination reaction, it gives cis alkene as a product. You can see here both should be anti with respect to each other. Base will abstract this proton and Br will go as a leaving group. You'll get a product where transalkene will be a major product. If I use SR diastereomer. If I take RR, then this is how the reaction takes place, and you'll find that the product is a cis product is obtained as a major product. So the diastereomers will give you different products if the mechanism followed is a E2 elimination reaction. So SR will give you trans, RR will give you cis olefin as a product. So we have understood now what is the E2 mechanism. We already studied about E1 mechanism. What you'll find now, if I compare E1 and E2, what is the difference between E1 and E2? E1 is unimolecular, E2 is a bimolecular reaction. Here, E1 takes place in 2 steps, E2 takes place in 1 step. A strength of base is not important in E1 reaction because we have seen that rate is directly proportional to concentration of substrate. Rate does not depend upon the concentration of base. But if you take E2, the rate is directly proportional to concentration of substrate as well as base. That means what type of base is used also affects the rate of E2 elimination. Generally, strong bases will favor E2 elimination reaction. Similarly, A1, in both the reaction, Sytzeff product will be favored because we know Sytzeff product is a more stable product. But if size of your base or size of living group is large, at that time, Hoffmann product will be preferred over Sytzeff product. No as specific geometry of the, because you get a carbocation as such. There is no steric crowding in even a reaction, but in E2 there is steric crowding because base and substrate both come together, and then in one step the product is formed. So what you'll find that anti-coplanar geometry is favored than syn-coplanar. That means your living group and the beta hydrogen should be opposite to each other. That is called anti-coplanar. In E1, since carbocation is formed and stability of carbocation becomes most important, then at that time rearrangement is possible to get the most stable carbocation, and accordingly then product will be obtained. But this is not possible in case of E2 elimination reaction. You will never get any rearrangement products. So with this, we come to an end of E2 elimination reaction. These are the various problems based on E2 elimination reaction. Kindly go through and try to answer these questions based on today's lecture. Thank you. In the next module, we'll be talking about a new mechanism, that is E1CB mechanism, as well as we are going to compare between again E1, E2, SN1, SN2, how they differ from each other, and which reaction will occur. That we'll discuss in the next module. Thank you.